Hi, in this video we're going to explore section 2 from chapter 10, talking about a specific type of potential energy that we're all familiar with, gravitational potential energy. So let's think about gravitational potential energy. The figure at the right shows a ball of some mass moving upwards from an initial vertical position that we can call yi to a final vertical position that we're going to call yf. So we have a vertical coordinate system y. We know that the gravitational force then is this downwards force coming from the interaction of the ball with the earth. So let's define the system to be the ball plus the earth, including their gravitational interactions. So here's our system. We have the ball that's going to change position relative to the surface of the earth. This then introduces an energy of interaction, right? The gravitational potential energy, UG, we can define as the work done by that downwards pull on the ball, okay, plus the work done on the earth. And again, we have to have a minus sign to get that as the, that the force, if it's aligned with it, it's going to push energy into the kinetic system, into the kinetic part of the system, and so that would be taking away potential energy. So remember in our definition, this minus sign comes in here to get the exchange between kinetic energy and potential energy correct. Let's calculate what those two pieces are. Well, WE is practically zero since the Earth has almost no displacement. So if we're thinking about the motion, remember the work is the force times the distance. The Earth isn't changing position here. And so WE we're going to take to just be approximately equal to 0. What about for the ball? We know that the force is minus mg, this constant downwards force near the surface of the Earth. So if we use our definition of work, we can find that gravitational potential energy change is going to be equal mg times the change in position y. Okay. So the ball is moving upwards by some distance. Notice that the force is aligned against the displacement. So that means we'd be doing some negative work, so then the potential energy would end up being positive as I move that object upwards, or I have a positive displacement. The change in the gravitational potential energy is mg delta y. Okay. Notice importantly that this is a change in the gravitational potential energy. Okay. That doesn't mean if we start at position y and leave it at the same position, that there's no potential energy available in our system. It means that the potential energy is staying static and not changing. So we can define gravitational potential energy as an energy of position. Okay. At some fixed point in a given coordinate system, we can say that the gravitational potential energy associated with that position is just mg times the position in that coordinate system. And then as my system evolves, we can write down that the total energy inside of my system is just going to be the sum of the kinetic energy of all the parts plus the sum of the gravitational potential energy. And this sum is the total system energy, and it will not change as time goes on as long as the system is isolated and has no external forces acting on it. So the initial sum of kinetic energy plus gravitational potential energy has to equal that final sum of kinetic energy plus gravitational potential energy. Now, the 0 point, right, from this definition, right, you can see it depends on the position. But remember, positions are defined in coordinate systems that are just choices that an observer makes. So the 0 of potential energy is some arbitrary quantity or arbitrary position that gets defined by how I set up my measuring apparatus or my coordinate system. So for instance, here's Amber and Carlos. They use coordinate systems with different origins to determine the potential energy of a rock. Okay, so for instance, you can see that Amber sets the origin of her coordinate system at the ground, where Carlos sets the origin of his potential energy to be a meter off of the ground. Okay. So Amber would say, well, my potential energy initially for this rock is 9.8 joules. And Carlos would say the potential energy of the rock initially is equal to 0 joules. And notice that no matter where they put the rock, Amber's value for the potential energy will always be 9.8 joules larger than Carlos's. Okay. So if the rock then moves, notice that they'll both calculate exactly the same change in potential energy. Right? Imagine we move the rock down. Well, now Amber would say that the rock has 0 potential energy because it's at her 0 point, and Carlos would say it would have negative 9.8 joules of potential energy. And if they took that final potential energy minus the initial potential energy, they would both find that they've lost 9.8 joules of potential energy. So we can see here that really the thing that's physically significant is the change in the potential energy, not the value of UG itself. The absolute values or the quantities of UG depend on our coordinate system, and those are free choices. But if I take differences in potential energy, then multiple observers using different coordinate systems will agree on how the potential energy is changing. And that's great. That also means they'll agree on how the kinetic energy is changing and the work that is being done on the system. Okay, so just keep that in mind, that when we're solving these problems, the potential energy for you or another classmate might be different if you're picking different coordinate systems, but in the end, if you're taking differences in potential energy, that should lead to the same energy analysis and the same final results of the problem, the same physical changes to the dynamics of the problem for both observers. So let's think about this idea. If I have a ball that's tossed up in the air, this simple bar chart below shows how the sum of kinetic energy and potential energy remains constant as the pebble rises and then falls. Okay. So here initially I have the ball pointing upwards. I'm defining my origin to be the ground here, so there's no initial potential energy, a lot of upwards kinetic energy. Now as that gravity pulls down on it, it's slowing the ball down, so I can see the kinetic energy is decreasing. And at the same time, it's getting further away from the ground, so my mg times y is increasing. And you can see the sum of these two bars is equal to 0. When I reach my maximum position, my maximum height, I have no velocity, so my kinetic energy goes to 0, but then my potential energy will be equal to my kinetic energy. And then as the ball turns around and comes back down, the potential energy again shrinks back to 0, and the kinetic energy grows to that initial amount. Notice here that the gravitational potential energy shown for a system like this, where a particle is moving at an angle while acting on by gravity, can be calculated by thinking about the work, right? The work done by that gravity, we know the formal definition is going to be Fg dot displacement. Let's calculate what that is. That's going to be, it's the dot product. So it's the x component of gravity times the displacement in x plus the y component of that gravitational force times the displacement in y. The x component is equal to 0 because gravity points entirely in y, and I end up that the work being done by gravity is just mg delta y. So because the force of gravity has no x component, notice that the work only depends on that vertical displacement of an object. So if I take an object and I move it horizontally and keep it at the same fixed position, I'm not changing the gravitational potential energy. It's only that change in the direction aligned with gravity that leads to changes in the gravitational potential energy. So consequently, the change in gravitational potential energy depends only on vertical displacement. Let's look at another interesting example here. So this figure shows an object sliding down a curved frictionless surface. The change in the gravitational potential energy of the object plus the Earth system depends only, again, on the change in the vertical position. the distance the object descends, not on the shape of the curve. Notice that that normal force is always perpendicular to the box's instantaneous displacement and doesn't do any work. So if there's no friction in this case, right, then the kinetic energy is going to remain constant, except for the extra energy that's going to go into it from the change in the gravitational potential energy. So if this object slides down this ramp, it's going to speed up as it goes, and that extra velocity that it ends up with on a frictionless ramp is just going to be equal to the amount of gravitational potential energy lost during that transition. And notice if I change the shape of this curve, as long as I start at the same initial and end up at the same final y, I'll have the same change in gravitational potential energy, and therefore I'll end up with the same speed at the bottom of the ramp. So if I add in friction then, friction increases the thermal energy of the system. And we defined it to, right, include both objects. So friction times the change in distance, I can be heating up the ramp and that ball here. So for a system that has both gravitational potential energy and friction, we can write down a more complete energy principle here. That if I have some initial gravitational potential energy and kinetic energy, later I can observe that my system has some final kinetic energy and some final potential energy. And if there was heating coming or some change in the thermal energy coming from friction, then the sum of the kinetic and potential energy will no longer equal to the initial sum of kinetic energy and potential energy, because the balance has gone into increasing the thermal energy of my system. We call the gravitational potential energy and the kinetic energy the mechanical energy of the system. And it is not conserved if there's friction. So I can lose mechanical energy to friction. But the sum of all that, right, if I capture all the energy terms, I still have a total conservation of energy. And because the change in the thermal energy is always greater than zero as a system evolves under friction, the final mechanical energy can be less than the initial kinetic energy. So that's a good thing to note. In a real system, if we measure mechanical energy and notice that it's altered during the system, we could ask ourselves, well, was there some thermal energy and where did that friction come from to try to improve our system? So some fraction of that initial kinetic energy and potential energy is being transformed into thermal energy during this type of motion. Okay, thank you. That's the end of our discussion for this section.